All right, so functional groups refer to groups of atoms that have a characteristic chemical or physical properties. So whenever we look at organic molecules, we're going to look at these particular functional groups, which is going to help us kind of classify them, group them together, talk about kind of reactions that they're involved in, so on and so forth. So for instance, a functional group could be an alcohol or a ketone or a carboxylic acid or things like that. And we're going to go through a bunch of these that you're going to need to learn and memorize moving forward. Um, so this is the part really where you just kind of have to do some memorization. You're going to have to make flashcards and kind of memorize and force yourself to understand what these particular functional groups look like. So in describing functional groups, common like chemical terminology is kind of shown down here in this shaded region where it says are bonded to a functional group. So this R often throws people off. That R is basically meaningless in terms of the functional group. All that R is saying is there's some extra carbon stuff attached to the functional group. So extra carbon stuff could be one extra carbon, it could be 100 extra carbons, it could be a ring of carbon atoms. So don't really worry about that R group in particular. You're more focused on what that functional group is. And as we look through and look at more of these structures, you'll understand what this means. Um, so a functional group can be a heteroatom. It can be something like that has an oxygen, or it could be a halogen, like a fluorine or a bromine. It could be something that has a multiple bond. It could be like a double bond. And sometimes it's going to be both of those. Like a very common one that we're going to see is going to be when we have a carbon double bonded to an oxygen. So that's, for instance, would be a heteroatom because it has an oxygen and it would have a double bond. So we're going to look at a whole bunch of these functional groups on the upcoming slides. So hydrocarbons are going to be the first functional group that we look at. And this is really what we're going to study kind of here in chapter 10 and also in chapter 11. We're going to look at it as well. So hydrocarbons are going to be molecules that have only carbons and hydrogens. That's why they're called hydrocarbons. So alkanes only have carbon-carbon single bonds. They're also going to have hydrogens there, and all the hydrogens are always single bonded. But the idea here is that all the carbon-carbon bonds are single bonds, and there's no other functional group there. So really, alkanes don't really have a functional group per se. They're just carbons and hydrogens with no multiple bonds. Alkenes, on the other hand, are going to have a carbon-carbon double bond. So that's going to be an alkene. So their functional group would specifically be that double bond right there. All right. Alkynes have a triple bond as their functional group. So specifically, it's when you have a carbon triple bonded to another carbon. So alkanes, alkenes, and alkynes are all molecules that only have carbons and hydrogens. And the alkynes down here on the bottom have a triple bond. Alkenes have a double bond. And then the last one here is called an aromatic hydrocarbon. An aromatic hydrocarbon is also frequently referred to as like a benzene ring. And what this is, it's going to be a 6-membered ring with 3 double bonds. So you can draw this really a couple different ways. You can draw it like this. And the 3 double bonds are always alternate in their locations. It doesn't matter where you have those, so I could draw it that way. I could also draw it. So there's a 6 one, and this time I'm going to alternate kind of in different spots. You could also draw your 6-membered ring kind of this way. You get the idea, right? So any 6-membered ring, so those are all carbons, where you have 3 alternating double bonds. So double bond, then skip a spot, double bond, skip a spot, double bond, right? And you can even see the aromatic hydrocarbon drawn on this slide as well. But these kind of show you your functional groups. So these are the ones we just talked about: alkane, alkene, alkyne, and aromatic hydrocarbon. Um, and this just kind of shows you in general what the structures will look like. So for an alkane, it's going to be only carbons and hydrogens. So an example here is where you have the CH3 and a CH3. Let me just come up here. So this one would look like carbon. So I'll draw it out as a complete structure like this. Right, so that would be your complete structure where you have two consecutive CH3s. And an alkene has the double bond in it. So the alkene shown there has your carbon-carbon double bond, and you can see the hydrogens attached to make sure that all the carbons have 4 bonds. Alkyne has the triple bond. So in those cases, you only need 1 hydrogen to make sure that your carbons have 4 bonds. And then you have your aromatic hydrocarbon on the bottom. And if you look down here at this depiction of it, you can see that because of the way this is laid out, every single carbon has 1 hydrogen attached to it. This is the reason why those double bonds alternate, because it creates this structure where basically all the carbons end up being the same. Each carbon is going to have a double bond attached to it and a hydrogen, right? So if you look at this particular carbon, it has a double bond going this way, a single bond going that way, and then a hydrogen up top. And every single carbon you look at there will have a single bond, a double bond, and a hydrogen. All right, so that's the aromatic hydrocarbon, which is also, again, frequently referred to as this benzene ring. Okay, so those ones are really the simplest ones because there's really there's no heteroatoms involved. It's just going to be carbons and hydrogens and looking at the various number of double bonds, right? Alkene had a double bond and an alkyne had a triple bond. So here are some functional groups that contain a heteroatom, and all of these are single bonds to a heteroatom. So alkyl halide, that halide word there is kind of refers to a halogen. So anytime you have a halogen attached, we refer to it as an alkyl halide. This alkyl word basically means you have an alkane, right? So you could have a 1 carbon long chain, you could have a 2 carbon, a 3 carbon, a 10 carbon long chain. It doesn't matter. You have a carbon chain attached to it and then attached to a halogen. So in the case in this example here, there's a bromine attached to it. So that's going to be an alkyl halide. The next one down is an alcohol. So an alcohol is determined by anything that has this OH group. So it's going to be anything that has a carbon single bound to an OH group. And that OH group is often referred to as a hydroxyl group over here. So if you hear the term hydroxyl group, the hydroxyl group is specifically referring to that OH. And the overall compound, the overall molecule you're looking at, would be referred to as an alcohol. So alcohol will have an OH group, and that OH group is specifically that hydroxyl group. In ether, so an ether is one we're not going to look at a whole lot, but I still want you to know what it is and be able to pick it out. But it's where you have kind of an oxygen that has 2 single bonds to carbons. So it's very similar to an alcohol, but an alcohol only has 1 single bond to a carbon, and then the oxygen is bound to a hydrogen, right? So for an alcohol, there's a single bond to a carbon. Remember, this oxygen right there is actually bound to that carbon if you were drawing it out. Let me actually come up here and draw that out as a complete structure just so you can see it. So it's going to be carbon. The CH3 would look like this. And then OH, right? And then those O would have the lone pair of electrons, right? So that's the alcohol. Now for an ether, it would be almost that exact same thing, except instead of the H, right, you would have another CH3 there. So the O would be specifically bound to the carbon. All right, so that's an ether, an oxygen in the middle of two carbons that are single bonds. And the last one here is going to be an amine. An amine is when you have a carbon bound to a nitrogen. So again, if we were to draw out the complete structure of this, remember it's CH3, and that carbon would be directly bound to the N. So that would be NH2, and then we would have a lone pair. And the reason I'm drawing these out is just to make sure that you understand whenever you look at this structure right there, it can easily appear like that the nitrogen is attached to the hydrogens, and it's really, really important that you understand that that nitrogen is bound to the carbon and not the hydrogens directly, because then the hydrogens would end up with more than one bond, which breaks the rules, and we're not allowed to break the rules. Right, so an amine is when you have a carbon with a single bond to a nitrogen, right? So again, this slide shows you four separate functional groups, all of them with carbons bound to a heteroatom through a single bond. Okay, and that brings us to functional groups containing the C double bond O group, which is called a carbonyl group. So a carbonyl group is anytime you have a C double bonded to O, and this is going to be really important because a lot of functional groups, basically the rest of the functional groups we're going to look at, all have this carbonyl group. So this carbonyl group is going to be found in many different types of compounds. So let's just go ahead to the next slide and kind of look at a couple of them to start with. So aldehydes and ketones, we'll look at both of these kind of in more depth whenever we talk about sugars. But in this case, an aldehyde has a carbonyl group, which is the C double bond O, attached to a hydrogen. So it's C double bonded to O, bounded to H. And again, notice I'm not talking about that R group because those R's are just extra carbons there. So C double bonded to O, bonded to H is an aldehyde. And I guess one thing I should probably say about these functional groups, you always start with this carbon that's in the middle. So even if we go back to the previous slide, or over here, right, you're always starting with the carbon to see what it's attached to. So in this case, we always had like the R to X, or R to OH, or R to O to R, or R to NH2. The fact that that R is just a carbon is important, right? Because whenever we go to the carbonyl groups and look at these ones, the R is attached to a C double bonded to O. So it's attached to that carbonyl, all right? So that's going to be an important thing to pick up on. So again, an aldehyde is C double bonded to O bonded to H. And then a ketone is when you have a carbonyl in the middle with carbons on both sides. So basically, a ketone is very similar to an aldehyde, except over here you have another R group, and that shows up over here, right? So the aldehyde has an H there, a ketone has a CH3 there. Although a ketone could also be, for instance, C double bonded to O bonded to, I could draw this as CH3, CH2, and on this side I could put CH2, 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 CH3. So I guess my point to this is that what you should really be looking for is, okay, you find your C double bond O, and that's going to be important. And you're like, okay, I have a carbonyl, what's it attached to? It's attached to carbon on this side and carbon on that side, which means it has to be a ketone. If it was attached to a carbon on one side, but then a hydrogen on the other, that's when it would be an aldehyde. So again, first thing is you pick out that carbonyl group, and then you see what that carbonyl group is attached to. And on this slide, it talks about the aldehyde and the ketone. However, there is still more functional groups with carbonyls. So we have, on this slide, we look at a carboxylic acid and an ester, and these two are related to each other. They're both very similar. In this case, both of them have a C double bonded to O, bonded to an O, And then in a carboxylic acid, it's C double bonded to O bonded to OH. And then in ester, it's C double bonded to O bonded to O that's attached to another carbon group. So again, very similar to the aldehyde versus the ketone that we just looked at on the previous slide, where the aldehyde ended with an H and then the ketone had another carbon group. With the carboxylic acid and ester, you have C double bonded to O bonded to OH, right? Which is what we're looking at over here. And then in the ester, you have C double bonded to O bonded to more carbon groups. And again, the number of carbon groups on all these examples is just put a CH3 group there just because to keep it short. That could really be a CH2, CH2, CH3. It could be any other types of carbons attached to it over there. So again, carboxylic acid and ester both have C double bonded to O, bonded to an extra O, and then an H. Or C double bonded to O, bonded to O, then a CH3. Right? Carboxylic acid and ester. And then we have one more. We have an amide. So an amide and an amine are very similar to each other. An amide and amine, anytime you hear either of those, you should be thinking about nitrogen, right? An amide has a nitrogen atom, an amine has a nitrogen atom. The difference here is that an amide, the one that ends in an IDE, has a carbonyl group. So in other words, a carbonyl attached to a nitrogen is going to be an amide. An amine is when you have a carbon attached to a nitrogen, but not the carbonyl group. So an amine is when you have a nitrogen bound to a carbon through a single bond, but that carbon cannot be part of a carbonyl group. So the easiest thing to look at is if you have a nitrogen, you should be thinking, oh, I have an amide or an amine. Okay, you look to see if that nitrogen is attached to a C double bond O. If it's a C double bond O, if it's an amide, if it's an N that's bonded to a C without the double bond O, then it's going to be an amine, right? So a carbonyl is going to be the amide, and then a regular carbon is going to be the amine. Okay, so all those functional groups we just talked about, you need to memorize and be able to identify to do problems that look like this. So what functional groups are in each of these? So in aspirin, we'll start with. So the first thing I do is I look around and I kind of look for any heteroatoms or any C double bond O's because I know those are going to be particular functional groups. So the first one I see is right here with the C double bonded to O bonded to OH. All right, so I see a C double bonded to O bonded to OH, and I say that is going to be a carboxylic acid. And again, problems like this are better to practice after you've gone through and tried to memorize those functional groups, right? You memorize them, then you need practice kind of identifying them in actual structures like this. So the next thing I see in aspirin is this six-membered ring that has the alternating double bonds. This one is called an aromatic hydrocarbon. And it could also be referred to as a benzene ring. Right? So both of those are ways you could describe that. And then the last thing I see here in aspirin is going to be this guy over here. I have another C double bonded to O bonded to O. So this one is very similar to a carboxylic acid, but it's not a carboxylic acid because a carboxylic acid is C double bonded to O bonded to OH. This time I have C double bonded to O bonded to O bonded to more carbon. So whenever I have that and I have kind of a carbon on one side and I have a carbon on another side through the whole thing, this one is going to be an ester. All right, so in aspirin, we have a carboxylic acid, an aromatic hydrocarbon or a benzene ring, and we have an ester. Okay, so now let's look at Tylenol. So let's look at a different drug on here. So the first thing I notice here is I have an OH, right? An O single bound to a carbon, that's going to make this one an alcohol. Or you could say, you could also call that OH specifically a hydroxyl group. Okay? And the next one here we're going to have is the aromatic hydrocarbon. Same thing as over here. Notice that on the one in Tylenol, they have all the double bonds kind of on the inside of the ring, and over there on aspirin, they had this one double bond there kind of on the other side. I'm not sure why it's drawn that way in these structures. It doesn't matter if you put those double bonds on the inside of the ring or the outside. Usually you'll see them on the inside of the ring. Okay, so in Tylenol, we have one other one here. We have a C double bonded to O bonded to an N. So remember on the previous slide, I said an N should grab your attention. And whenever you have an N, you either have an amide or an amine. And basically you're looking at, well, is that N attached to just a regular carbon or is it attached to a carbonyl carbon? A carbonyl carbon being the one with a C double bond O, which is what we have here. And if it is the carbonyl carbon, then you have an amide. Okay? And then, so that's it for Tylenol. So now let's go down to Advil, which is the last one on the page here. So in Advil, we have C double bonded to O bonded to OH, which is going to be a carboxylic acid, right? Same thing as this one up here. And then we also have this aromatic hydrocarbon. So all three of these pain relievers and fever reducers have aromatic hydrocarbons as part of their structure. And then in Advil, if we look at the rest of the molecule, it's all carbons and hydrogens, so there's no other functional groups there. So all three of these have aromatic hydrocarbons. A couple of them have carboxylic acid. We also see one with an ester, one with an amide, one with an alcohol. So again, I picked these structures because they cover a lot of the different functional groups that we're going to be looking at here. So again, go through and practice your functional groups. Make sure you're able to identify them in particular molecules.